All right, we're going over last minute part 3 FRQs, but we're doing number 2 in this video. We have a table of values here. We also have a graph of h given and also information about f of x. So let f of x be defined as provided here. G is a twice differentiable function, so we don't see what the graph of g is. We're only given listed values, but we know that our g graph is going to be a nice smooth curve. No sharp turns, no holes, no asymptotes. Our table is given for values of g. G and g prime are given, and also h is a function that's defined using linear portions, linear segments. For part A, find the slope of the line tangent to the graph at x equals 1. So if I want to find the slope, all I need is to find the derivative, and from the derivative I evaluate the derivative at x equals 1. So I didn't have to find the point. Initially I thought I had to find the equation of tangent line, so there's no need to find the point here. We're just going to move directly to the derivative first, and then we can evaluate the derivative. So let's look at each of these terms here. The sine of u becomes cosine of u times u prime. Natural log of u becomes u prime over u. So once we have our derivative expression, I'm cleaning it up a little bit here, push the pi out in front, and now I can plug in, evaluate at 1. So plug 1 in for x, I get pi cosine of negative pi minus 1 over 2 minus 1. This becomes just negative 1 for the second term. This first one, cosine of negative pi, is the same thing as cosine of pi, which is negative 1. Negative 1 times pi is negative pi. So we have negative pi minus 1. We'll leave it in this exact form as our slope value. For part B, let k be defined as h of f of x plus 2. This f of x plus 2 is all contained within the h function, so we need to recognize this as, if we want to find the derivative, it says find k prime of 1, we have to recognize this as chain rule and not product rule. It's not h of x times f of x plus 2. This is a function inside of h. I'm going to rewrite it, make it more visually easier to distinguish. This f of x plus 2 is contained inside this h, so I'm using bracket to make it easier to see. Now we have to find the derivative. So derivative says outside function's derivative times inside function's derivative. So the outside portion is my h of x. So apply chain rule. We have the outside portion, which is h parentheses, and then the inside portion is the f of x plus 2. So we take turns with each of these function. Outside, h parentheses becomes h prime parentheses or bracket, and then we move on to the inside. F of x becomes f prime, and then 2 goes to 0. So, and then we fill in the bracket with what we see inside the original bracket. All right. Now we have an expression that represents the derivative. We can now evaluate the derivative of k at 1. So now we can plug 1 in for x. So h prime of f of 1 plus 2 times f prime of 1. I need to resolve this f of 1. So to find f of 1, I'm going to plug 1 into the original function. And I did that here for part A. I didn't need it initially, but it looks like it ended up being something that I can use. So I'm just going to plug in 1 in for my function here. So I get sine of pi plus natural log of 2 minus 1, which is natural log of 1, which is 0. So sine of pi is 0. Natural log of 1 is 0. So 0 plus 0 is 0. So replace f of 1 with 0. 0 plus 2 is 2. And now I'm able to clean that portion up a little bit more. F prime of 1, we have that information from part A, so we'll just drag that down. So we have h prime of 2 times negative pi minus 1. H prime of 2, let's see, how can we get that information? We have the h graph in front of us. H prime of 2 must be asking for the slope of the h graph at 2. So this is a nice linear graph here, so we can just find the slope of that line. And that will be consistent all the way through. So if I just pick 2 points on this line and just do slope, rise over 1, down 1 over 3, so my slope is negative 1/3. h prime of 2 is negative 1/3 times negative pi minus 1. I can leave my answer in this form, or I can distribute through. Either way is fine. Part C, evaluate the definite integral from negative 5 to negative 1 of g prime. So let's see, g prime, we could go through using g prime and find the area under the g prime graph using Riemann sums, but it's not asking for an approximation, it's asking for the exact value. So what we're going to do is we're going to bring that g prime up to a g of x level, and then we can simply use subtract the g of x values to find what we need with the to evaluate this antiderivative. So we're going to apply first theorem. So g prime is going to move its way up to g of x, and we can plug in our upper and lower bound. So for this problem here, our upper bound is negative 1, our lower bound is negative 5. So once we make that evaluation, then we can look at our table. G of negative 1 is just 1. G of negative 5 is just 10. So G of negative 5 is 10. So 1 minus 10 is negative 9, so that's our answer. Part D, evaluate the definite integral from negative 1 to 4 of h of x. So we have the h graph in front of us, and these are all nice geometric shapes, so we can just find the area between the graph of h and the x-axis and keep track of our positive and negative regions and total them up. So we want to go from negative 1 to 4. So from negative 1 to 4, we have this triangle region, and these two triangles here. So 1/2 base times height, we get 1/2. 1/2 base times height for this triangle here, that's 1/2 3 times negative 1. We know this is going to be a negative region here, so negative 1.5. This is a really small triangle, 1/2 times 1/2 times 1, so that's going to be negative 1/4. And this is equivalent, except it's a positive, so negative 1/4 and positive 1/4, they're going to cancel each other out. We're just left with 1/2 minus 1.5, and that's going to reduce down to negative 1.